13.5. The chain rule. Suppose an economist modeling the output of a manufacturing system uses a production function where L represents labor, K represents capital, and R represents natural resources. Suppose L is a function of the unemployment rate, K is a function of the prime interest rate, and R is a function of time. Then the relationship between the variables can be charted this way. Suppose the unemployment rate increases by 0.1% and the interest rate decreases by 0.2%. What is the effect on productivity? In this section, we develop the tools needed to answer such questions. For now, we will go back to the model of a hiker on a hyperbolic paraboloid. Suppose z is a differentiable function of x and y, where y and x are differentiable functions of t. How does a change in t affect z? Let's say this over again. A change in t creates a change in both x and y, which in turn creates a change in z. An extended form of the chain rule tells us how a change in t affects z. The choice of notation is important. We write z partial x because z is a function of both x and y. We write dx dt because x is a function of t only. And we write dz dt because ultimately z is a function of t only. Let the surface be a hyperbolic paraboloid and let the xy coordinates be given by these equations. Find dz dt and evaluate at pi over 4. All right, let's stop for a moment. The parameterization of x and y is a circle in the xy plane centered at 0, 0 with a radius of 2. The surface the hiker is on is a hyperbolic paraboloid, and he is walking in a circular path. Z of t is his elevation at time t. All right, let's go back to our problem. We set up the derivative. We find z partial x, z partial y. Find dx dt, dy dt. Use the parameterization to write dz dt as a function of t. And then simplify and evaluate at pi over 4. At time pi over 4, the hiker is on a steep climb down. Suppose z is a differentiable function of x and y, where x and y are differentiable functions of t and s. Create a tree diagram to show how a change in t or s affects z. Z is a function of both x and y, which in turn are functions of s and t. If t changes, the effect on z is given by z partial t. If s changes, the effect on z is given by z partial s. Let's evaluate z partial t for this function and parameterization. We set up the partial of z with respect to t. Find z partial x, z partial y. Find x partial t, y partial t. Then we insert the expressions given for x and y and simplify. Last topic for today. Given this expression, we define f in this way. Then the original equation is given by f equals 0. We can treat x as the independent variable and differentiate both sides of f equals 0 with respect to x using the chain rule. If we do that, we get a nice formula for dy dx. It's equal to the negative of f partial x divided by f partial y. And we can use partials to find dy dx.